Hey, this is Jay Slusser, and this is my data science project. I thought I would be starting my data science project off doing some market basket analysis for a personal project, which has been pretty fun, so like a grocery shopper. After browsing Yellowdig, I found a post about someone wanting to do food security, so I kind of hopped on that train, and I was introduced to a food security lab here through Nick. I was able to get some really interesting data on food security and able to analyze that in relation to Vermont, which I think is pretty cool. As a Vermonter, I was able to get some Vermont data and analyze that, and it felt kind of personal, more than just making somebody richer with data science tools. I was able to actually have an impact and guide some processes, which is pretty cool. And right here in Vermont, which is similar to what I've been doing in my other lab, where I do a lot of COVID modeling work, and that also works with some really smart people in the lung lab and med school there, and we have to do some cool work. But enough for that, and we can get right into it. This data set is actually two surveys combined, kind of horizontally, and each survey has about 200 plus questions, and they all are questions relating to food security. So maybe questions about where you get your food, how food secure you are, income, where in the state you are, how you get your food, and a lot more. So like, are you assisted with food? And the first one was sent out in late March here, you can see. And the other one was sent out, if I scroll over and find it, oh, I went too far. I still went too far. In late May, early June, is when it is. Oh, there we go. Right there. Perfect. And I got to do some natural language processing with this data and also do some logistic regression. So we'll get right into the natural language processing part. And what's also great about this data is that it came with a code book. So the code book here actually explains all the variables, chunks them together. So certain variables were all transport related and had different or similar variable and information here, and same with other variables like snap. So they were more agree versus binary for a few of these. So that was super helpful. So what I got to do for the NLP pipeline was super cool. I got to look at a column called Other Worries, which is a column relating to worries that either weren't covered by the survey, which is super useful because as people who create the survey, they can use that information to create better questions in the future based off of uh, those other worries, and also um, able to help look at like composition of like what people were worried about that wasn't on the survey at different times, which is what I was able to do using this Jensen-Shannon divergence, which I'm pretty sure is actually made by someone at the UVM Complex Systems Department. I'm not sure where they are now, but I'm pretty sure it came from here, or at least a presentation in it. So super cool to use a UVM tool to solve a UVM problem. And what this does is compare how surprising words are in a given context at time one and time two. So the example that this package uses on like a presidential speech for two presidents, and it compares like what was being talked about in one versus the other. So I was able to use that methodology on what people were worrying about at time one versus time two. If we go ahead and run it, all I do is a bunch of string cleaning here, standard NLP stuff, lemmatizing, stop words, tokenizing, and then I do a little word proportion too, but it's not super useful because there's a lot of words that only appear one time. So if we look at this graph here, it's super cool. It's kind of like a stacked bar graph almost. And what we can learn is that at time one, so this is around late March or early April, people were talking more about like how they're getting their food inside of their houses. You can see they're worried about contamination, wiping down and sanitizing food, getting exposed. Look at that, we got rice down here, and a bunch of other words. And these are more useful to researchers in context, so not necessarily just looking at like, oh, this word is surprising here versus how meat is more surprising in time two, which it was actually, and that's pretty interesting because if we were to break it down and look at what was happening around June 1st, is that I think that's actually when the mask mandate hit. So people were definitely talking a lot more about masks in June than they were in late March, early April. So it's super cool to see that like right there in the data. And you can see this little backtick here. There's a huge problem with data where Python doesn't like quotes within quotes. So my solution was that just replace all the single quotes with backticks because it's still readable, um, but it gets rid of a problem. So it was super cool to compare these two texts and realize that, like, hey, people were worried about a lot of different things at these times. So there's a lot to uncover there. And I tried with a few other columns, but there just wasn't enough similar words to draw any meaningful insight. There were a bunch of other text columns, actually, uh, which I'll show you in the change security script here. And this is all about using logistic regression to try and predict how somebody's food security would change over time. And it's not useful in terms of building a model that does that. It's useful in terms of figuring out like what variables are important. Because as people who can impact food security in Vermont, you want to be able to target that impact and not just work on something that may not be valuable, but actually find something that is related to food security and actually work on that. So a bunch of cleaning had to be done here actually. I went manually and dropped a bunch of these columns, and I went from about 487 to 400, I think. What we're trying to predict actually is change in food security here is what I call it. And you take their food security of the year and take that away from how food secure they were in the last 30 days since COVID. And if that was a positive increase, we make it a 1. And if it was no change or a negative increase, we make it 0. So logistic regression can be used to solve this problem here or model it. And what ends up happening is all the text columns need to be dropped. All the columns that aren't useful, so like references, dates, languages, aren't useful. There's definitely some drawbacks. I think I just haven't had enough experience with logistic regression to encode everything I need to, and also I lose a lot of data imputing. I think there's definitely ways to impute data better, especially missing data, because I lose about 2/3 of my data set after I impute everything, drop all the columns I don't need. There's still about 2/3 of observations with like missing data, and that's not super useful, but it still is data we can use. So when we go ahead and run this model, I don't really graph anything or do anything too much with it, just because it's uh, not super useful. Um, we're not trying to like pinpoint something. We're just trying to find like what's useful, right? Predicting how accurate it would be is not useful. And we get a wicked accuracy actually of 0.86, which is nice, but it's not super useful. And this is all precision recall to help with false positive, false negative, whatever in model improving. But what's actually important is these coefficients here. So if we scroll all the way to the bottom, we get the most positive ones. So this is a USDA column, and a lot of these columns could actually be combined into a single column. So you could combine, say, how somebody was feeling about in this variable in time 1 versus time 2, and just take the difference of that, which I didn't do, which could save a lot of time, or at least shorten the width of my data set. But overall, there's still 400 columns that we have to go through, and in this model. But and even the USDA ones, I think they have a specific metric that can be used. So what I mean is that if I were to spend more time, which I plan to do, I can make this model a lot better. So in the coming weeks, I think we're going to push this into a publication, or at least a publication, and I'll be able to have some figures in there, which will be cool. But also, if this model were to go in it, there's some lot more improvement that needs to be done, such as SMOTE. So there's a lot more urban population represented in this data set, which doesn't reflect Vermont's actual population distribution. So we can use SMOTE to kind of fix that, and which allows us to create more sort of dummy variables or dummy observations for underrepresented categories in the data set, and also could use recursive feature elimination because there's a lot of features that aren't useful, right? If we go more to the middle of this here, we see what, like 0.0, right? That's not useful for us. But what it does tell us is that a lot of these variables were actually super important, right? And that makes sense right here. So worry, food unsafe, right? If you're worried your food is unsafe, you're probably not going to want to buy a lot of food, which is going to lead to food insecurity. If you're worried about having enough food that already is related to food insecurity, right? If you're just worried about having enough. So sort of things like that, and these numbers will mean more with the SMOTE and feature elimination and better imputing happening. It's just that that takes time and a lot of domain knowledge that I have to build up. But overall, that's what I was able to do for this data science project, was sort of take these two questions and sort of answer them, which is pretty cool. And they'll definitely get better. But overall, thank you, and that was my presentation.